Welcome to this lecture on algebra. Today, we are going to explore a fascinating and beautiful concept known as the nth roots of unity. Imagine standing in the center of a perfectly circular room. If I asked you to turn around in exactly 3 equal steps, how would you do it? This simple idea of breaking a full circle into perfectly equal, evenly spaced steps is exactly what we will be doing mathematically today. Let us dive in. Before we look at any equations, let us understand why this concept matters. In mathematics, the word unity is simply an old-fashioned term for the number 1. When we talk about the nth roots of unity, we are looking for special complex numbers that, when multiplied by themselves a certain number of times, bring us right back to our starting point of 1. Because of the fundamental theorem of algebra, an equation with the highest power of n must have exactly n solutions. So if we want the fifth roots of 1, we are looking for exactly 5 unique numbers. Now that we understand what we are looking for, let us look at how we represent the number 1. On the complex plane, the number 1 sits at a distance of 1 from the center, with an angle of 0 degrees. But angles on a circle repeat. Every time you make a full rotation of 2 pi radians, you end up in the exact same spot. Therefore, we can add full rotations to our angle without changing the actual position of the number. The letter k acts as a counter for these full circles. This trigonometric expression is correct, but it is quite long to write out every time. This brings us to Euler's formula, which beautifully connects angles to exponents. By using the base of the natural logarithm e, we can write this long expression in a much cleaner, compact way. This compact exponential form makes multiplication and division much easier. We can now substitute this flexible expression for 1 back into our original equation, setting us up perfectly to solve for the unknown variable z. To isolate z, we need to undo the exponent of n. In the world of exponents, taking the nth root is the exact same thing as dividing the existing exponent by n. This simple division gives us our master formula. Let us break down the symbols. The variable z is the specific root we are calculating. The variable n is the total number of roots we want to find. Finally, the variable k acts as a step counter. It starts at 0 and goes up to n minus 1. As k increases, the angle increases, stepping us evenly around the circle until we have found every single root. Before we calculate specific numbers, let us look at what this master formula actually produces visually. Here, we see the fifth roots of unity plotted on the complex plane. Notice how the roots perfectly divide the circle into 5 equal slices. The first root, z0, sits exactly on the real axis at the number 1. As k increases, we step counterclockwise around the circle. If you connect the dots, they form a perfectly symmetrical regular pentagon. This visual symmetry is the most beautiful and useful property of the roots of unity. Now that we have our formula, let us see this with a concrete example. We want to find all the complex numbers that satisfy the equation z cubed equals 1. This means we are looking for the cube roots of unity, so n equals 3. We will use our master formula and plug in k equals 0, 1 and 2 to find all 3 roots. For our first root, we plug in k equals 0. The exponent becomes 0 and any non-zero number raised to the power of 0 is exactly 1. This makes logical sense because 1 times 1 times 1 is simply 1. We have our first root. Now we move to the second root by setting our counter k equal to 1. This gives us an angle of 2 pi over 2 radians, which is exactly 120 degrees. To find the exact coordinates on the complex plane, we need to convert this back to standard form using sines and cosines. The cosine gives us the horizontal position, which is negative 1/2. The sine gives us the vertical position, which is positive root 3 over 2. This places our second root in the top left quadrant of the circle. For our final root, we plug in k equals 2. This gives an angle of 4 pi over 3 radians, which is equivalent to 240 degrees. We again use the cosine and sine functions to find the exact coordinates. Both the real and imaginary parts are negative, placing this root in the bottom left quadrant. We have now found all three cube roots. If you plot them, they form a perfect equilateral triangle, perfectly spaced 120 degrees apart around the circle. Let us solidify our understanding with another example. Now let us find the 4 complex numbers that satisfy z to the power of 4 equals 1. We set n equal to 4 and we will let our counter k take the values 0, 1, 2 and 3. Just like before, plugging in 0 for k gives an angle of 0, resulting in the number 1. This is our starting point on the far right side of the circle. When we move to k equals 1, the fraction simplifies to an angle of pi over 2 radians, which is exactly a 90-degree turn counterclockwise. The cosine is 0 and the sine is 1, giving us the imaginary unit I. We have now completed 1/4 of our journey around the center. Next, we will find the root that sits exactly opposite to our starting point. Setting k equals 2 gives us an angle of pi radians. This is equivalent to a 180-degree turn, meaning we are facing the exact opposite direction from where we started. The cosine of pi is -1 and the sine is 0. This places us on the far left side of the horizontal axis. The third root is the real number -1. This makes perfect sense because -1 multiplied by itself 4 times is +1. We just need one more step to complete the shape. For our final root, we use k equals 3, which gives an angle of 3 pi over 2 radians. This is a 270-degree turn, pointing straight down to the bottom of the circle. The cosine here is 0 and the sine is -1. This gives us our final coordinate of -I. If we plot all 4 roots, they are 1, I, -1 and -I. They form a perfect square on the complex plane, with each point exactly 90 degrees apart. We have successfully sliced the circle into 4 equal pieces. Now that we have calculated these roots, you might be wondering why they matter. These roots are the mathematical foundation for the fast Fourier transform, often called the FFT. The FFT is an algorithm that breaks down complex signals into simpler waves. Every time you stream a video, listen to digital audio, or connect to Wi-Fi, your device uses the FFT to process the data quickly. The nth roots of unity make this possible because their perfect symmetry allows computers to skip millions of redundant calculations. Without these perfectly spaced numbers, modern digital communication would be far too slow to function. Let us review what we have learned today. The nth roots of unity are the n distinct complex numbers that equal 1 when raised to the power of n. We find them by dividing a full circle into n equal slices using angles and Euler's formula. These roots always lie on a circle of radius 1 and form a perfectly symmetrical regular polygon. They beautifully bridge the gap between geometry and algebra, making complex digital signal processing possible in our modern world. You have now mastered the fundamentals of the nth roots of unity. Great job!